This is the Linear Motor Drive project. My name is Wu Binghua, and my advisor is Professor Chen Hongqi. For contents, first, control architecture. Second, component introduction and testing. Third, issues encountered during testing and attempts. Fourth, conclusion. Linear motors have many applications in daily life, such as major door systems, CNC machines, and maglev trains. This type of motor produces linear motion rather than rotation. This project explores and attempts to control a linear motor using FOC, field-oriented control. The goal is to operate the motor using only current loop. What is FOC? Field-oriented control, also known as vector control, is a control technique used in variable frequency drives for three-phase AC motors, such as brushless DC motors. In this method, the stator current is mathematically transformed into two perpendicular components. One component is responsible for establishing the motor's magnetic flux, while the other produces torque, based on the desired flux and torque, typically generated by the speed control loop. The control system computes the corresponding current references and regulates them independently. This simplifies the control process. FOC is relatively efficient compared to other methods, therefore gaining wider adoption. This is the control loop. First, the two error signals are fed to PI controller to become BQ and VD. These two signals are fed to transformation to become VA, VB, and VC. These three signals are fed to SPW module to become instructions for the inverter. Inverter uses these instructions to send power to the motor. To obtain angle information for these two transformations, I use an encoder. To provide feedback information for the control loop, I use a sensor to detect the current information. The information first go through an ADC, then a transformation, then become IQ and ID, therefore completing the loop. Let's start the component part with current ADC. The voltage output from the current Hall sensor must be converted into current value. To achieve this, I use the HAS50-S sensor. The sensor was wound 5 times, so the actual current value is amplified by 5. This means that 10 amps correspond to 4 volt output voltage. I set the scaling vector accordingly, so that input 4 volts gives 10 amps in the control loop. For Park's transformation, because signals in a three-phase AC system vary over time, we simplify them into time-invariant components for easier analysis. This is Park. This is inverse Park. Here are some encoder types. Incremental encoder only provides relative position. In a linear encoder, the scale is a straight line with alternating black and white stripe. One black-white pair generates one pulse. Knowing the length per pulse allows position calculation. Z signal marks the zero position. If we cut this disk and stretch it to a line, this will be linear encoder. For rotary encoder, the disk is circular with alternating black and white stripe. One pair generates one pulse, the same. However, the signal here indicates a full rotation. This slide is about the motor. I use the LMCB4 linear motor. The full travel of the mover is 320 millimeters. Permanent magnets on both sides of the track have alternating polarities. So one side is N, the other side is S, the other side is N, this side is S. Each NS pair along one side is a pole pair. The length is 32 millimeters. One pole pair is equivalent to one permanent magnet synchronous motor rotation. So one full travel, the 320 millimeter, equals 10 revolutions. This is like a two-pole motor where electrical angle equals mechanical angle. And the spec of the LMCB4 linear motor is provided here. For motor and encoder, the encoder outputs two pole signals 90 degrees apart, shown here, 90 degrees apart. Detection counts rising and falling edges, rising, falling. So degrees per pulse is 360 divided by 32,000 equals 0.01125. Let's talk about offset elimination, which is very important. Motor phase sequence of this motor is U, V, and W. The encoder must align with the U phase back EMF. Back EMF waveform is minus sign. The following is motor back EMF equations. So let's see this equation. And this part is this part. And it turns out this part is the motor's back EMF. So let's see these two charts or graph. The green line is back EMF. The yellow line is encoder signal. And in this graph, there's offset. And in this graph, this is with correction, so there's no offset. SPWM is used to generate inverter control signal. And when sign is greater than triangle, the output is 1. Otherwise, output is 0. Changing sign frequency changes output frequency. So let's see. When sign is greater than triangle, the output is 1. When sign is greater than triangle, output is 1. And when sign is lower than triangle, the output is minus 1. And when sign is lower than the triangle, the output is minus 1. So 1. And that's an inverter. So it's 1, 0, or 0, 1. This part is the implementation. TIF2A335 is used for control signal generation. Here. Driver circuit shown here amplifies control signals. Power stage is shown here. This is the full wiring diagram. This is the motor. For open loop test, I set VQ to 0.5, VD to 0, using a custom rotating angle. Load is Y-connected resistors and inductors to simulate the motor. By saying VQ and VD, I mean VQ and VD. In this test, there is no feedback, so open loop. The purpose of this test is to verify the SPWM module, the inverter, the driver, and phase sequence. This shows phase sequence. This is phase A, phase B, and phase C. These are voltage. And this is the current and voltage of a phase. In this case, this is phase A. Let's step into the issues and the implementation part. And let's begin with FOC, the current loop test. In this test, the motor is connected and ID is set to 0 while IQ is set to 0.5. Ideally, current should not have these spikes. So, this graph is graphed when the motor is running. The yellow is RIQ, green is RID, blue is IA. And let's see IA. There should not be these pronounced spikes in current IA. There's some issue here. There's more issues in current loop test. First, errors remained large regardless of Kp and Ki. Second, no load current cannot reach 0.5 amps target. Many spikes and noise are observed. Third, ADC conversion ratio are found higher than theoretical value. However, after the conversion ratio is corrected, the errors are still large, so I switched to open loop test. Oh, by the way, the picture on the last page, this one, has its conversion ratio corrected. Also, This one has its conversion ratio corrected. And let's see this graph. So blue is IA, yellow is feedback IQ, and green is feedback ID. And ideally, we will want IQ to become, in this test, 5 volts, and ID become 0. And we can observe that ID is sort of 0, so kind of okay, but IQ is definitely not okay because it is far from 5 volts. The video you just saw comes from the open loop test with encoder feedback. And in the test, ID is expected to be about 0, but in reality, the result is sinusoidal and a little bit far from 0. It's like about 1 volt, etc. So initially, I suspected that Park transformation has some error. However, I later verified that no, Park transformation part works fine. And later, finally, I discovered that the ADC feedback lags the clamp measurement by about 74 degrees, which is quite large. And it is likely that the ADC input circuit has some issue. And sadly, the problem exceeds this project's scope, and moreover, there's no time for debugging. And let's see this graph. The blue line is current A from the clamp meter. The yellow line is current A from the ADC. And we can see clearly that the ADC one lags the clamp one a lot. The video you just saw was from the software attempts. As I mentioned on the last slides, there's no time for debugging the circuit. However, I have an idea. I'm certain that theta E is correct. However, from the IA, IB, IC standpoint, theta E is incorrect because I know that IA, IB, IC all have a delay about 74 degrees. So, from a MATLAB simulation, if there's a angle delay in inverse Park transformation, the Q and D value will drift away from their intended value. My thought was that, well, how about I implement 2 theta in this control loop? One is the original, correct theta E. One is this theta E minus 74 degrees to become this theta E. So, in effect, I want to add an angle delay to this theta E. By adding an angle delay, I can match the degree in this transformation. So probably moving the D value and Q value back to their intended position. Maybe this will solve the problem. Let's see. Well, sadly, this just somewhat solved the problem. So Kp can be reduced from 13 to 10, while Ki from 1 to 0.3. However, I still cannot reach the target, ID and IQ. The large delay is suspected to be the culprit. Here you can see IQ should be 0.5, but it is in actuality far from 0.5. And ID should be 0, but now it is even lower than 0. And debugging the circuit is the only option. However, sadly, there's no time to do so. I also found that there's some more issues, like the motor actually moves faster and faster as I implement more and more trial. Like, for example, you can see that, well, the IA current becomes more and more erratic as time goes by. And in fact, the mover moves faster and faster. It will accelerate to a point that it will be fast enough that it will not significantly accelerate more. And what I suspect is that the delay causes normalized VQ to increase over time, and this will cause overmodulation. And overmodulation will produce this erratic current pattern. And also, as Charles goes on and on and on, noise also increases, as well as the acceleration and the speed. Well, in fact, the delay differs slightly between three phases. It's between 74 to 68. In conclusion, feedback delay prevents expected response. Hardware fix is required. Second, delay likely causes normalized VQ to exceed 1, causing overmodulation. Third, debug ADC circuit for successful experiments. Fourth, if overmodulation still occurs, consider adding a limit to the PI controller. Fifth, test each hardware component before integration. Sixth, beware of bias. Stepping outside of a rabbit hole may save lots of time. In fact, I should have suspected that there is an angle delay in the ADC circuit. If I had found that this delay exists, I may have enough time to debug the circuit, therefore completing this project. This is the reference part. Thanks for your attention. Wish you have a good day, and goodbye.